Hey folks, I got some examples involving impulse and momentum to do with you. The first one involves a baseball. The mass of a baseball is approximately 142 grams. I looked it up. So let's say that the ball is pitched toward you, and let's say here it is, and it's moving this way horizontally. And just to throw a number at that, let's say that velocity is 30 meters per second, which would be about 66 miles an hour, so not terribly fast. And let's say you hit it really well and the ball comes flying off your bat, and its velocity when it comes flying off your bat is 40 meters per second at an angle of about 35 degrees above the horizontal. Now, I just looked the times up for a baseball bat collision, and they're very small. So I'm going to round it to 1 millisecond, which is 0.001 seconds. Okay. Some of the sources I saw actually saw even a slightly smaller number, like 0.0007 or something like that. So I'm going to round to 0.001 seconds, though. So what we want to find here is what is the impulse imparted to the ball and the impulse imparted to the bat. And then what's the force on each one, the ball and the bat. Okay. So for impulse, you can do force times time. And we do have a time, but we don't know the force. So we have to use the other half of the equation, which is impulse is change in momentum. Okay. Now, what's absolutely very, very critical here is that we establish a positive direction in this situation, both horizontally and vertically. Now, since we're hitting the ball left, I'm going to go with left as positive. It doesn't really matter, but I'll go with left as positive, and I'll also go with up as positive. So that will be my little coordinate system for this one problem. In order to find delta P, okay, that's going to be m delta V. In this case, the m is not changing. It's the V that's doing our changing. All right, so V naught would be negative 30 I hat, and V final would be, I got to do my cosine and sine, right? So if I do 40 cosine of 35, I get 32.77 I hat. And then it's going upward at 40 sine of 35. And for that, I get 22.94 I hat, or J hat, sorry. So delta V, change in momentum would be M, which is 142 grams or 0.142 kilograms times, okay, V final minus V naught. So I've got, in the I direction, I've got 32.77 minus 30, which would be 62.77 I hat, and then plus 22.94 J hat. Okay. And if you distribute your mass in there, I got 8.91 I hat plus 3.26 J hat. The units are kilogram meters per second. Now, I never asked you specifically for the change in momentum, but that also equals the impulse acting on the ball. Okay, so that's the impulse acting on the ball. Now, what about the impulse acting on the bat? Well, here's the beauty of this. It's Newton's third law. For every force, there's an equal and opposite force. Impulse is just force times time. I hope you'd agree with me that if the bat is hitting the ball for 1 millisecond, that the ball is also hitting the bat for 1 millisecond. So the impulse on the bat and the ball will be equal and opposite. So the impulse on the bat, all you got to do is switch the signs of each of these. So it'll be negative 8.91 I hat minus 3.26 J hat. Kilogram meters per second. I won't rewrite that. Now, for force, okay, it doesn't matter which one I look at, the ball, the bat, they're going to be the same size, just opposite direction. I'll go with the ball for now. So force is impulse divided by time. Now, we're assuming the force is constant throughout this collision. It turns out it's not really constant, but let's pretend it is. So all I got to do is take this and divide it by 0.001. So all I got to do is move my decimals 3 to the left. So it's going to be 8,910 I hat plus 3,260 J hat newtons, okay? And the force on the bat would be the opposite. Just put negative signs in front of both of those. And then you could also Pythag those to find the magnitude of the force acting on the ball. If you do that, you get about 9,490 newtons, okay? And by the way, that's a big number. That's roughly 2,130 pounds. So that's a lot of force being exerted on that ball. Okay, so there's one example. The next example I have for you is, in this example, mass didn't change. It was a ball. Okay, the next example, I'm going to actually have one with mass changing. Let's say you got a rocket ship. Okay, so here's the rocket ship, and it is throwing gas out. Oh, by the way, quick note, a rocket ship does work in outer space. The fuel actually has oxidizer in it, so they burn no matter where you're at. And basically, it's a conservation momentum thing. The rocket's throwing gas downward, or pushes gas downward, and the gas pushes the rocket upward. So it works no matter where you're at. So let me give you the following data. Let's say we have our rocket. Now, these things are very large. Let's say the mass is 2 gigagrams, okay? And let's say the velocity of the gas coming out is a roughly 4,000 meters per second. And let's say the rate at which the gas is leaving, we call it m dot. That means the mass over time, or the rate of change of mass of the rocket, how quickly the rocket's losing mass, is 7,350 kilograms per second. Now, by the way, that's a large number. It's a couple cars per second coming out of this large rocket. With that data, what I want to calculate is what's the acceleration of the rocket, okay? Well, like all things where you have multiple forces acting on the object, you probably should draw an FBD. So here's our FBD. You're going to have two things acting on the rocket. You're going to have the force of the gas pushing up on the rocket. That's called thrust. I'll just call it F sub T. That's not tension, it's thrust. And then, of course, we're on Earth. There's gravity. So there's the force of gravity acting on the object. Now, the force of gravity is easy. You're just going to do m times g. The force thrust, that's where you're going to use your impulse momentum relationship. So impulse, which is Ft, equals delta mv. And if I want force, I'll get that by itself. We got delta mv over t. Well, in this case, what's changing is the mass per time. The rocket's losing 7,350 kilograms each second. That's how quickly the fuel comes out. So your force is simply going to be, well, this is just m dot. So it's 7,350 times your velocity, which is 4,000. And I get, I'm going to leave it in millions. I get 29.4 meganewtons. So that's million newtons, okay? Now, the force of, so that's this number right there in our FBD. The force of gravity, well, that's mass times acceleration of gravity. The mass is 2 gigagrams. We need to make that into kilograms. It goes kilo is 10 to the third, mega is 10 to the sixth, and giga is 10 to the ninth. So to get from 10 to the third to 10 to the ninth, it's a 10 to the sixth, which is a mega. So this is 2 mega kilograms, okay, times 9.8, and you get 19.6 mega newtons. Now, if that bothers you, you can just convert this to kilograms, and you're going to get 19.6 million newtons, which is fine. But it's kind of nice to do a shortcut this way. All right. So now, if I want to find the acceleration, I do net force equals ma. You've got force of thrust minus force of gravity equals ma. The force of thrust is 29.4 meganewtons minus the force of gravity, which is 19.6 meganewtons. This equals, it's 2 million kilograms, which is 2 mega kilograms times A. So what you'll notice is all the megas cancel out here, okay? And so you end up with 9.8 equals 2A, and so A is 4.9 meters per second. Now, that's not a terribly large acceleration. That's half of gravity. If you ever watched a rocket launch, when it's first leaving the pad, its actual acceleration is usually not that large. You kind of wonder sometimes they're going to actually make it off the pad. But the cool thing is, as the rocket accelerates upward, several things change, okay? So first of all, the force of gravity becomes less as you gain altitude, because little g decreases with altitude. Also, the mass of the rocket decreases with altitude. So both of those lead to a greater acceleration. So as time goes on, the acceleration of the rocket actually increases. All right, well, I've got another couple examples for you in the next video. Hope this was helpful, and I'll see you in the next one.